ray diagrams is where we draw an arrow that represents the light ray and then shows what happens to it. So, for example, if you have, if you have your light going into the mirror like this, here's your light ray, it hits the mirror and it bounces off the ray of light. So whatever this is, like light or whatever you want this to be, your light. So what that means then is that's called reflection. We all know how that works because we look in a mirror and we see our face and it's reflected in the mirror or whatever. A mirror is reflection. And there's some very special properties. It turns out that this angle right here is always equal to this angle, always when it's reflected. If it's refracted, it passes into a substance. So what happens is I have something like water, and here's my light ray, and it hits the water, and then it bends, goes into the water. And I have this dotted line here, and this dotted line here, that is called the normal. Kind of like the normal force. So this is the normal. And this is the normal. And always you measure things relative to the normal. So this angle here has, these two are the same. These two are the same. These two are not the same relative to the normal, but they have some properties that are related. So either we have reflection, that's how mirrors work, or we have refraction, that's how lenses work. So the first part of this, we're going to learn about reflection and refraction, etc. And then later on, we're going to do the practical application of, okay, here are mirrors, what do we do? Here are lenses, what do we do? Now, they talk a little bit about something called constructive and destructive interference. And so what happens is, when you have a light wave going along like this, and you have another light wave going in the exact opposite direction, it's not very opposite, what happens is, those end up canceling each other out. So in a little more, like a simplified version, if I have one pulse like this going this way, and another pulse like this going this way, when they overlap, I might get this. But then they keep on going. Then I have this one at the bottom continuing, and the one at the top continuing. And that's called destructive. Interference. Constructive is where you have this one going this way, and this one going this way, and they overlap this way. That's too tall. This one and this one, so they're going towards each other, and when they overlap, you get like A, B, A, and B. This is A, B. This is A and B. Here's B and A, continue. And then this one goes to B, A. And it keeps going that way, and this one goes that way. So constructive means you add, like they add together, but it's like this one is a negative in destructive. So we have those properties. There's something called diffraction and something called polarization, which we'll talk about yet later. So basically what we're going to do is we're going to focus on when it strikes, when a wave of light strikes a solid barrier, like a mirror. Some or all of the particle is reflected. And basically what happens is the ingoing ray is called the angle of incidence, and the one that's coming out is called the reflected angle. So the angle of incidence always equals the the angle of reflection. And they're always measured relative to the normal. So on a test, you might get told the angle in the ray makes an angle with angle of, let's say, 40 degrees to the mirror. And the question is, what's the angle of reflection? Now, that looks like, oh, 40 in, 40 out. But this one is saying, I'm giving you this is 40. Right? Be careful when they don't say it's the angle of incidence, it's the angle to the mirror, that's 40. So that would mean this is 50, which means this is 50. So the questions are not meant to be tricky, but it's meant to be that you have to be careful. Are they giving you the actual angle of incidence? What's the reflected angle? The same. Or are they giving you the angle with the mirror? Now, when this is like, some of these are like interesting practical applications. So when you have light hit any surface, it always bounces off with that same angle. But what happens is, if you make the surface, and I tried to exaggerate this on a molecular level, really rough. This surface here is really rough. When the red light ray comes in, it hits down here somewhere, right down in here, and when it bounces off, those two angles are the same, but it's coming back up. So we've got these parallel light rays going in right here. This one, this one, this one, all parallel. But when you look at what the ray that comes out, they're not parallel because when they've hit the surface of the substance, they're hitting on different edges of that roughed up surface. And so the light ray spreads out. Now, here's the kind of, some of this is kind of cool and simple practical application. If you've ever driven on a rainy night and you're like, why the heck does it feel so dark? When you are driving in the rainy night, the water, now let's make it blue. The water makes a thin little surface on your pavement. So your headlights hit this nice smooth surface, and all the light bounces up in the same direction. But if you're driving on a pavement that's dry, your light rays come in and they might bounce off like this, or they might bounce off like this, or whatever, and they spread out, and you actually see more. So on a dark, rainy night, it is darker in your car because your headlights are all getting bounced off in the same direction. When you're driving in the dark on a dry night, your headlights are hitting the rough pavement and the lights are going all over the place. So you actually, oh, I can see in the ditch. I can see wherever. So it's still the same property of light. It's bouncing off with the same angle it came in, but it just depends if the surface rough or not. Okay, so again, refraction is when the light passes into another substance. So here's my light ray. It hits, it's coming from air going into glass or water, and it bends. And there's an angle of incidence, an incoming angle, but instead of a refracted angle, it's called instead of a reflected angle, it's called a refracted angle. And there's a relationship between them two, and it's always measured with respect to the normal. And so here's the formula this for refraction, and this is important. Whenever you're dealing with this formula, when it changes, when a substance goes, if I shine a light from air into water, remember the speed of my voice is fixed by air, but as soon as I change it into another substance, the speed changes. So the light speed will change in water, but the frequency won't change. So if I change the substance, the speed changes, but not the frequency. Frequency is constant even if I change the media. And if you think of it, it's like this. If I hold a skipping rope and I shake it, and let's say the skipping rope, now that's in the air, now there's some jello. It's still wiggling the same because I'm still moving the same, right? The thing that's making the wave, the source of the wave, is still wiggling the same frequency, no matter whether it's in jello or water or air, and that's what frequency is what is the thing that's making it. If you don't change from red light to green light, you can't change the frequency. If you change from red to green, then the frequency is different. So here's this little formula now. Here's what the sine of the angle, that's obvious, velocity is obvious, lambda obvious. What's that m? It is called index of refraction. And it's just a number that compares the bending of a substance compared to a vacuum. So let's just have a look at this. Like, I got this greasy little jar of oil. Have a look. It's a jar of oil, nothing exciting, right? It's a jar of oil. Absolutely nothing fun. Just a greasy, slimy jar of oil, right? We agree? Jar of oil. Nothing interesting, jar of oil. Right? Just a jar of oil here. Right? Jar of oil. Ordinary jar of oil here. Now this is where physics is magic. I'm going to make magic happen. Jar of oil. And I'm going to tell you how to make kids go, oh my God. Jar of oil. Nothing exciting. So I go, abracadabra. And I reach in here and I go, oh look. Invisibility does really happen because, no, it wasn't just a jar of oil. There was a beaker inside there that you couldn't see. The reason you couldn't see the beaker is the index of refraction, the N of bending of light for this oil, is exactly the same as this Pyrex glass. So your eyeball can't tell the difference. Now, what I've done before, but I can't do it because I hate breaking the beaker, for when you have middle school kids, is you pretend you're doing something, drop the beaker, oh my God, I broke the beaker. And then you clean up the pieces, you go, but I've got magic solution, or elementary kids, really good, right? I've got magic solution that's gonna make this glue back together. And then you make sure the beaker is big enough, and obviously you've got the real beaker that's not broken in here, and then you put your pieces in around the edges. They all disappear, and then you go, and then you reach in and you pull this whole beaker out, and the kids are like, whoa, right? So that's funny. So this, in other words, invisibility is real. So, and then the other thing I think is actually fun to think is this room could be full of aliens with the same index of refraction as air. We can't see them. They know that this is the party classroom to be in. They're all like, yeah, physics. We got to come and find out about physics. They could be sitting right here with you. Or Harry Potter's invisibility cloak. That's not just a movie. That's real. Well, okay, I wish it was, but we know what we're getting at. So the idea then is that N is the amount of bending. All right, pass. Okay, so again, we have this formula that we'll get to that's for refraction. This is a little summary on constructive and destructive interference, where when they overlap or superimpose, you get that particular thing happening. And then standing waves, we'll talk about that, those two things will come back. So now we're here, and again, we're looking at reflection. So reflection says the angle of incidence will equal the angle of reflection. So that is saying this angle here, we usually call the angle of incidence, or theta 1 if you want, and this is theta 2 or whatever, however you want to call it. So this is angle of incidence, and this is the angle of reflection. So there,